So the angle between two lines. So previously we've done the angle between two vectors, and we've had this formula here. Cosine theta equals the dot product of the vector A and B divided by the length of A and B, where A and B are two vectors. Now for two lines, we're going to find the acute angle between them. So we use the formula cosine theta B1 dot B2 over the length of B1 B2. Now that might not make sense for the minute, but what we're actually looking at here is we consider these lines here and here. I'm just going to make it a bit clearer. The direction vector B1 is the direction vector. B1 equals direction vector of line 1, and this one here, B2, equals the direction vector of line 2. Now, I'm gonna find an example that works for this later. I'm gonna double check with an example, but these are the direction vectors here. And so it's not, obviously a line goes on for infinity. So we're just looking at those components will give us this angle here. So this angle here, theta, is acute angle. Okay, which means you could figure out this one here or this one here. Now, in 2D, the lines will cross unless they're parallel. But just be aware that in 3D, we're going to go into this more later, but for the minute, we're just going to be practice calculating these. But in 3D, you're not actually guaranteed that the two lines might have an angle between them, but they might not intersect. All right. Now, our next notes here are parallel and perpendicular lines. Consider two lines where we've got pretty much our equation for our vector equation for a line here and vector equation for a line here. If the direction vectors are a scalar product, if B1, if the direction vector of one of the vectors is a scalar multiple of the other, then they are parallel, and we use this notation to state they're parallel. If they're perpendicular, the dot product, which should make sense, if the dot product equals 0, cosine theta equals 0, which means they are cosine 90 is 0. So that means they're perpendicular. So let's have a look at this. So find the angle between the lines. We've been given these two lines here. So we need to consider our direction vectors of these lines. So at the moment they are in parametric equations, but we might consider line 1. I'm just going to write it as R1. It's going to obviously equal 2 and -1 plus it's got t as its vector there, and we've got -3 and 1 here. Now 1 is this value here. So this vector here is our B1, our direction vector. We've then got our L2 is going to be given by R2 equals 1 -4 plus, now they've picked S as the variable, so S, and then we've got 2 and 3. And this here is B2, which is a vector as well. So now we've got the direction vectors. So now cosine theta is going to equal the dot product. So I'll write this out. I'm going to skip this step a little bit later because we're going to run out of time. So got these values here, B1, B2. Now, because I'm super lazy, let's just jump to the next one. So we've got -3 times 2 is going to give me -6. So -3 times 2, we're going to get about over here. That's going to be -6. And then we're going to have plus 1 times 3, which is going to give us +3. So this top here is going to equal -3. Oh, but I've got the absolute value here, so absolute value bars. which means this is going to equal positive 3. Now, let's do the denominator. Now, that's pretty poor working the way I jumped around like that, but I'll fix it up now. B1, so we're going to do 3 squared plus 1 squared. So we're finding the modulus of the direction vector plus 1 squared, and then that will be times by 2 squared plus 3 squared from the other direction vector. All right, so this is going to equal, or not so far, we're going to have 9 plus 1, so we're going to have root 10, and root 4 plus 9 is going to be 13, okay, over square root 130. So we're going to end up with 3 over root 130. Now you've got to remember that this is cosine, so we need theta inverse cosine, and we're going to put this value in here, which is 3 over square root 130. And if I put that in my calculator, I'm going to get, I should have got my calculator out. So cosine, what have we got? 3 over square root 130 equals 1.3. I'm in radians, so I better fix that. 1.3 doesn't sound right, so do that again, and I get 74.7. So if we think about those two lines that are crossing there, now obviously I'm not drawing these properly with their slopes, but we've got here that these acute angles here are 74.7 degrees, which means 180 minus our other answer. We've got these ones here. Let's change colour. This one here would be 105.3, or I could change it to that one. All right, now you also have the benefit here that we can use our calculator. So our GC, we do our option, math vector, and then we get to angle, and then in this space we can actually just put the two direction vectors in. So I'm just doing this for you. So if you go angle, bracket, and what did we have? We had -3 and 1, -3 and 1, comma, 2 and 3. So we're going to put that in. Now I'm doing this just so we've got these in a 2 by 1. No, I want, so just putting this in, -3, 1, comma. Now 2, 3, close bracket, and I've got, interesting when I did it this way, the angle without the absolute value in there, it has given me, it's given me the obtuse angle here. So I've got this bigger angle here when I did it in the calculator this way, but we can calculate them in the calculator. This will be, trying to think of why, this is not following the formula here for the angle between two lines. It would be calculating the angle, sorry, I'm just trying to see if there's another one I've missed. No, I'll come back to that anyway, but that's how we do it with the calculator. It's just giving you the obtuse angle there. Okay, next one here, let's look, find the angle between these. So we've got here, we've already got B1 is this one here. We need to figure out what B1 is here. You got to remember that these all equal a value here, so we could rearrange them. Now, usually if we get good enough, we don't need to, but we'll call this R2, which means it's going to have an X component. You've got to remember, This one here, let's just do mu equals 1 minus x on 3. This will rearrange to 3 mu and then plus not plus, minus 1 equals negative x, redo them, x equals 1 minus 3 mu. This one here, we've got y equals mu, and then the last one here, 2 minus x over 2 equals mu, which means we're going to have 2 mu equals 2 minus x, which means we then multiply by negative x is going to equal 2 minus 2 mu. So we can put these values in here now. So we've got 1, 0, and 2. So they're from my calculation. So I've got those values from this here, and then y, this can't have a value there. Let's, just because it doesn't have a constant there. And then we've got plus mu, and then we've got our direction vector is going to be negative 3, 1, and negative 2, which is B2. Now you can see here, negative 3, 1, negative 2, negative 3, 1, negative 2. So we've got here that not only are, they're not even a scalar multiple, these are actually, the direction vectors are the same once we break them down. This scalar in front could be different, so we would say here B1 equals B2, therefore R1, let's just get really, R1 is parallel to R2, and then what is this? Oh, it says find the angle, therefore angle between them is 0 degrees. Last one here, find the measure of the angle between them. So this one here is a problem where you get them in equations. So if we rearrange these equations here, we're going to have, one of the equations is y equals negative 2x plus 5. So this is, we'll call this one line 1, and then we've got line 2 here is going to be given by 2y equals 3x minus 8. Then we divide that, y equals 3 on 2x minus 4. So I've broken them into two equations. So this line 1 has a slope or a gradient of 1 over negative, okay, because you've got to remember here, this slope, I'm going to call it M1, is the change in y over the change in x, which means we've got negative 2 over 1. And then same with this one here, we've got M2 equals the change in y over the change in x, which equals 3 over 2. So this is the vector B1, the direction vector of this line, which is going to be given by negative 2 and, wrong way around, 1 and negative 2. And this vector here, B2, is given by 2, which is our x component, over 3. So you're sort of realising here that x is that one, x is that one, and then y is that one, y is that one. So a little bit different from what we've done in lines so far. Okay, so once you've got them, we're going to solve them the same as we have previously. You can ditch the video now. I'll finish the solution in the video, but you can get rid of it. So you don't need to watch me finish this because we've done it before, which is the same way we've done it. B2. Oh. dot product 1, feels weird not talking through these, 1 times 2 plus negative 2 times 3, and don't forget our absolute product. Okay, and then we've got square root 1 squared plus negative 2 squared, square root 2 squared plus 3 squared, and this equals negative 6 plus 2. Negative 6 plus 2 is negative 4. And then we've got square root 5, square root 4 plus 9 is 13. So theta is going to equal inverse cosine 4, we change it to a positive because it's an absolute value, and then 5 times 13. Over root 65. So inverse cosine 4 over square root 65 equals 60.3 degrees. So got that all sorted. Therefore the angle between the lines is about 60.3 is 60.3 degrees. Perfect. All done there. I could do with the calculator. Let's just quickly put it in the calculator, see if it comes out the same. Obviously, you might not be watching anymore. Negative 2. Yeah, so what do I get? Negative 1, negative 2, 2 and 3. It gives me 119, which is, it gives me the obtuse angle there again.